Welcome to APEC. It's May 29th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Benjamin Solomon will present alternative models to quantum theory. Jason Verbelli will be discussing Galiliean transformations and the work of Dr. Edward Dowdye. And Mike Gamble will be presenting on the Dean drive and rotating mass systems, as well as electromagnetic equivalence. After that, we'll catch up with the latest research from the Falcon Space Team and associates, and we'll be wrapping up the event with open discussion and ad hoc presentations. So just a few quick reminders. You can view conference replays, details, and speaker information on our website at altpropulsion.com. Please save your questions for the Q&A session after each presentation. Go ahead and type those questions into chat as they come into mind, and we will go through that chat and read them after each presenter finishes. So let me do this. I want to introduce you to our first guest. Benjamin T. Solomon is a member of the Nuclear and Future Flight Propulsion Technical Committee of the American Institute of Aeronautics and Astronautics, the founder of iSETI LLC, the founder of the Zotus One Foundation, researching interstellar propulsion physics and technologies. He's published numerous peer-reviewed conference and journal papers on gravity modifications and interstellar propulsion, and recently completed a 12-year study into the theoretical and technological feasibility of gravity modification. Today, he'll be presenting an in-depth review on an alternative physical model to quantum theory, along with insights and predictions that it offers into gravity modification and reactionless propulsion systems, such as Roger Scheuer's EM drive and many others. So Benjamin, welcome, sir. Let me ask you to unmute.
Right.
Wonderful. And I will hand it over to you, sir.
Okay, let's go. So that's what I'm, the last 10, 15 years, I've been working not just on gravity modification, but how it relates back to other physical properties. And I think many of you have seen this before. I discovered the first formula for gravitational acceleration that does not have mass in it. And I also showed that the gravitational constant is not a constant, it's a coefficient. It's inversely proportional to the isotopic mass of the element. And I proposed how nature implements probabilities. And that's basically what we're going to talk about and the consequences of that to Scheuer's M drive. How nature implements probabilities is not a question that quantum theory asks, or any other theory for that matter asks, but it's important to know that, because then we'll know how to manage probabilities. Because if we're going to do interstellar propulsion, that's the only way it's going to be done. Any form of gravity modification is still limited by Lorentz Fitzgerald transformation and Newtonian gravitational transformation. So as part of that, I had proposed a probabilistic wave function, which is an alternative to the Schrodinger wave function. And we'll get into that. And finally, the important stuff later on down the road is that probabilities and randomness are two different physical phenomena. Okay, some background. This is about 20 years of work altogether. I've put together about 7 publications. The latest is about, see, my industrial background is in finance, primarily in loss analysis for portfolios. So this is, I have a critique of Dodd-Frank, and it's to do with the risk retention criteria. But I've also put together a monograph on real-world modeling in statistics, in physics, and in medicine, because my friend has collected more than 10 years of his MS symptoms, and we were able to use that to reconstruct the disease processes. So we expect that to substantially hasten treatment or cure for MS. And going back to my background, I'm involved in the startup business AI models. AI stands for asymmetric information resolution. So if you know how to look at data, you can tell things from the data that most people cannot tell. And so my two monographs are about how do you look at data? Okay, is it a vacuum? No. What about space-time? In this section, when I looked at space-time, I realized that there are many different types of space-time. For example, and I don't use the word space-time continuum anymore because it's full, it comes with this whole lot of baggage, including ether. So to get away from all that baggage, I've called it keno, which is derived from the Greek meaning vacuum, kenos. So Einstein's keno is basically X, Y, Z, and T. And what I proposed in some of my earlier work is that there are actually 6 dimensions, X, Y, Z, T, the electric field, and the magnetic field. And this, conceptually, this concurs with Chandra Roy Chowdhury, who really stated for the first time in 2014 that space-time has to be a rich medium for a lot of things to be observable and to work consistently. And he goes into the explanation of why photonics analysis is segmented. One part of photonic analysis uses a certain set of theories which are not congruent with another set of photonic analysis. So the whole thing has to come together. If you look at physics, there are segments. There's no one quantum, for example, there's no one type of quantum theory. There are segments of quantum theory, but they all have the Schrodinger wave function as the underpinning. And that has to be, that segmentation has to be removed. One of the things I proposed was that subspace exists. It's only X, Y, Z. There's no T in it. And that is how nature implements probabilities. And the other version of a keno is the variable electric permittivity, which is very similar to space-time, but it is the space-time in the nucleus of an atom. And you can see this binding energy. And this took quite a bit of work to get there, but I'm not going to go into it. I'm just letting you know that there are various types of space-time that make the universe come together. Unlike quantum theory, which basically says there are different types of particles that make the universe come together. In my March presentation, I explained that space-time is the carrier of velocity and acceleration, and everything mimics, anything in space-time in that local space mimics the transformations present in space-time. Okay, how is gravity created? I'll touch on this a little bit to give a flavor of how broad this analysis has been. It's taken about 15, 20 years to do all this together. How is gravity created is not something that the physics community has taken seriously. In fact, if you ask any physicist, they will say they do not know. Okay, all they know is mass. But if we look at it deeper, mass is actually a proxy for the amount of matter. And the model I built was a quark model of the neutron and the proton. And this was prior to 2015, the up quark mass was 3.343 MeVs, and the down quark mass was 3.356 MeVs. But since then, I believe, if I recall correctly, there was a paper by Davis et al. Who changed that quark mass, and now that quark mass is the accepted view. The problem is, this is all theoretical analysis. So anybody can write a paper on what the quark mass should be, including myself. the reason why I say that the problem is it is not possible to empirically measure the mass of a quark because quarks do not exist outside protons and neutrons. So what I said was that to get the correct model using that variable electric permittivity matter, quarks are orbiting within the protons at 99.94% of C. And when you get that, when you put that velocity in, you get exactly the mass of the proton and the neutrons, depending on the combination of up and down quarks. So that's an indirect proof that the original pre-2015 masses of up and down quarks are correct. And then there is a step down. So you have the nucleus here. This is wet matter. And then you step down to space-time. And that step down will give you the gravitational field transformations right at that surface outwards. So now we have a version of a theoretical possibility of how gravity is created, which somebody else can come back and say, hey, I got a better version. It's falsifiable and we can test which is which. The next question was, why does conservation work? There are 4 consistencies. Energy, mass and energy are not conserved simply because they are not, are conserved simply because they are conserved. No, there's some underlying principles behind why it is conserved. And the first is the transformation consistency, which I show here. When space-time folds, you'll see the transformations change. And that transformation must be identical for all the 6 dimensions. The next step is the transfer consistency, which means if you have a particle in space-time, the transformations present in the local space-time is identically reflected by that particle. So those transformations are equal. The third is a spectral consistency. Basically, you have electron shell, and when the electron changes orbitals, it releases a photon, and that photon has a specific frequency. That frequency is independent of whether the electron shell is in a gravitational field or not in a gravitational field. And the proof of that is when we observe the spectral lines from an interstellar source, we can tell by the shift in the spectral lines that it is hydrogen. And that shift is consistent because the observation, the spectral lines energy are identical for any environment. And what the environment does as the photon travels through space-time is to change the frequency depending on the properties of space-time. And the 4th consistency is Kano consistency. That is, if there's a transformation in space-time, there is an equivalent transformation in subspace or in wet matter. And that's why, because of that, we can now say how probabilities work. So conservation is exactingly definite at any level of measurements. That's what I'm saying. And that's what nature exhibits. And in theory, over unity is not possible. But nature has a way out of that. So the next section is shedding some light on photons. We'll look at what the structure of photons are. So if we look at a transverse wave, there are 2 types of displacements. The edge of the electric or magnetic field moves up and down, and the motion vector of the transverse wave is either moving orthogonally. So the edge is actually a description of the transverse wave, but not of the medium. Another side note, which I finally, it occurred to me, it was staring me in the face. It's probably staring everybody in the face, and nobody really took it, paid attention to it. That the electric field lines and the magnetic field lines are not repelling each other. They're not repulsive. They are parallel. They don't repel. So there is a couple of questions. One is, how do you get a medium that oscillates between 0% and plus or minus 100%, which means within, if nature is definitely exactingly correct about the energy at any levels, any level of scale, then you cannot have a transverse wave where the energy goes from 0 to 100%. The total energy is the same, but individually, if you look at the electric and magnetic field energies, they're going from 0 to 100%, plus or minus 100%. So that doesn't matter. That current theory basically says that doesn't matter, but it does, because nature is exacting at every level of detail. So there is the next slide. I'll explain how to get around that, how to resolve that. But the point is that if the field lines don't repel, that means Poincare forces do not exist. See, if you have electron, you have these electric field lines coming out, and current theory says that there's repulsion between any two field lines, and therefore on the surface of electron, there are enormous forces. And so Poincare put forward the set of theoretical structure explaining why and how the electron structure, or for that matter, the proton structure, is stable in spite of these enormous forces. But if you say, you look at the transverse wave, the electric and magnetic fields, the lines are not repulsive, and therefore you don't need Poincare's forces. And so to test that out, what I did was I modeled electric fields that overlap. They don't repel, they overlap. And when you overlap, depending on the direction, the middle section either increases or decreases the density of the lines. And you can prove that the results are the same as classical electromagnetic theory. So there it goes. Electric field lines and magnetic field lines do not repel each other. There's some other property that's going on that we have to dig deeper to find out why they behave in such a manner. Okay, so the solution to the oscillation of 0 to plus or minus 100% of the electric and magnetic field energy is that it is the electric and magnetic field vectors are like a super vector that rotate between space-time and subspace. And therefore, what we see in space-time is a projection of this rotation between space-time and subspace. So you get a 90-degree phase shift between the transverse wave, the electromagnetic wave in subspace with the electromagnetic wave in space-time. And with that, you get the electric and magnetic fields are conserved at any moment in time. Okay, so you need subspace for this to be conserved. And okay, so coming back to quantum theory, so which would you believe? The discoverer could not explain how he came up with this wave function of particles, and if you look at it, the motion vector is down this way. It's coming down this way, and it is a wave function that is amplitude modulation with a damped oscillation. So this envelope, if you look at this crest and the troughs of the envelope, of the wave function, it's a damped oscillation. Versus what I had proposed was from the point spread function, you can derive a photon structure that looks like this. This is intensity, and that's the wave pattern at the back panel that is orthogonal to the motion vector. Okay, whereas with this version, you have the wave function moving like this, and the motion vector is in line with that wave function. So, okay, so Feynman basically said about Schrodinger's wave function, it's based on heuristic arguments, it's brilliant intuitive guesses, and even false arguments. But Feynman says that it does not matter. The important thing is that the equation gives the correct description of nature. Yes and no. If you look at shielding around 2010, I looked, maybe earlier, I looked at NASA's microwave shielding data done by a guy by the name of Otoshi, if I recall correctly. And I matched up all his results with mine using the probabilistic wave function. I gave it a name. This equation has been around. B, if you look at B, this equation has been around for about 150 years, but it's never been given a name. So finally gave it a name. It's a probabilistic wave function. You have the motion vector and you have a flat panel, which is the probability distribution of the particle, of the photon, and a motion vector sticking out like this. So in a sense, it's an umbrella shape. And all the probabilities are associated with the radial, orthogonal radius, or with respect to the motion vector. Okay, so if you deconstruct it, photon structure consists of four parts. The space wave, which is this piece here, on the side panel, and it's you see frequency modulation, high frequency here, and the wavelength decreases as you go out. Then you have a peak, peaks here, the probability peaks here along the axis of motion, right to the center of the axis of motion, it peaks, and it curves downwards with lambda over 2 pi r. R is the radius from the center of the center of the motion vector. And here that's the envelope function is lambda over 2 pi r, which is this, which is basically 1 over r. When I did my early work, I found out I used a sophisticated SATS package that was available on PCs, and I tested many distributions, and I finally found that there was a variable gamma distribution that would fit this curve, and I called it var gamma for short. But later on, when I started looking at the properties of the photon structure, I realized, hey, this equation from 250 years ago gives as good as fit, if not better. So why do we want to use a complicated function? So I adopted the probabilistic wave function. So this probability is actually a function of 1 over r, the orthogonal radius from the motion vector. And you have a transverse wave here in the middle. The thickness of the transverse wave is 0, because the transverse wave is an amplitude modulation with respect to the electric field and the magnetic field. It is not with respect to distance. So this central axis where the transverse wave exists is infinitely thin, because there's no dimension to it. And so you have an orientation which is either up or down or left or right, depending on the polarization. the space wave down here. And so there are 4 pieces: the space wave, the envelope function, the transverse wave, and the motion vector. Those are the 4 pieces to a photon structure, which is different from the Schrodinger wave function, because the wave function is in line with the motion vector. Now, the importance of this is, if we go back into history, Niels Bohr was asked why, when electrons orbit the nucleus, there's no synchrotron radiation. And from paraphrasing from what I recall, he said that's how it is. Now, with this model, if you have the nucleus here and the motion vector pointing this way, and so the orthogonal space wave is here and the electron is orbiting this way, as long as the motion vector points towards the attraction, the acceleration, there will not be a synchrotron radiation. So that confirms that this is probably the correct model of the photon and electron. But electrons have a mass, so it's a little bit more complicated, but this is the basic structure of what particles should look like. Okay, then I started researching and got a shock, because there are experiments which says that when a wave hits a surface, there's a phase shift with respect to either the transmitted. So you have the purple dotted line is the reflecting surface. If it passes through and some of it passes through, some of it gets reflected back, there is about a 90-degree phase shift between the incoming or the transmitted wave and the reflected wave, which is very shocking, because if you think about it, if there's a phase shift, you cannot make a standing wave. And the other problem with calculating standing waves is how fat is the photon. So the reason why I say that is, if we go back here, what is this length? What is this length of figure A? What is the length of this this wave? Because as the wave comes in and it hits, it reflects. The outgoing reflection will partially cancel out the incoming wave. So that will, if you want to be picky, all that will alter how your standing wave forms, if it's possible. Whereas with this type of structure, it's an infinitely thin, wavy, orthogonal plane, and it doesn't interfere with its, except for a minute fraction portion, when upon reflection, it doesn't interfere with the standing wave that's being formed. So, and then I came across this guy, and I'll play this. This guy, Bill Hammack, he explains microwave standing waves in Physics Lens. That's the website he presented this. So if you go to how microwave standing wave is produced, let's shortcut and go to right where it is.
This microwave
Here. Okay, he uses cheese to show the hot spots. Note there's no rotating plate.
Now, you can see on here sections where the cheese is completely melted and other sections where it's completely heated.
So
the oven's metal walls only reflect waves of a length that fits inside the oven. This standing wave causes hot and cold spots inside the oven. The three-dimensional pattern of waves is difficult.
Okay, so I hope you were able to hear that. What he said was, if you don't have the plate in here and you put the cheese in, very simple down to earth experiment, you will find hot spots within the cheese. And that is, those hot spots are the standing waves that you see here. So the second requirement is that the microwaves are jiggling the water dipole, the hydrogen plus and the oxygen minus. So what it does is it jiggles the dipole, water dipole molecule so that it heats up the water, because it's basically entropy is basically vibration, thermal movement. So what he shows in this graph is that the phase angle is consistent whether it's reversed or shifted, whether it's shifted or not shifted, which means that there's no phase angle shift in the microwave with respect to this type of surface. And the jiggling gets, because you get the jiggling of the water molecules because this crest becomes the crest becomes a trough and the trough becomes a crest, and they keep alternating. So it's technically it's not a standing wave, it's an oscillating standing wave, and that's how you get microwaves warming up the wave. And then you can look at a more complicated discussion, because the microwave won't produce exactly the same wavelength. There's a probability of distribution around it, so you get interference patterns coming through, and that could be another explanation. But really, we have now two sets of experiments. One says that reflection causes phase shift, and the other says reflections do not cause phase shift. So the only thing I can think of is it's the material that you're using that does or does not cause the phase shift, which becomes important later on for Scheuer's M-drive. So now that we have a theoretical approach, we can now falsify existing theories. Falsify is a technical term in physics, which means can you look at and compare what works and what doesn't work. And so we're not saying that the existing theory is completely false, nor are we saying that the proposed theory is completely true, but we can overlap and have a better perspective of how we do our measurements. Okay, so one of the things I showed was that if you have an object of a small radius and a photon, the orthogonal space wave of the photon, which is a big radius, and the bulk of that probability distribution, that orthogonal disk is within 2 meter radius of the axis of motion. The radius of the photon itself for 650 nanometers is about 10 billion kilometers long. So that's huge, but bulk of it doesn't have a significant probability distribution to affect things, which is unlike quantum theory, which basically says that probabilities go to infinity. No, they don't. So we have a radius of an obstruction, small r, and the radius of the photon is a big R. And we can say that shielding can be described by the log function of the probability of the radius, the big radius divided by the function of small radius. And this matches Otoshi's results, Otoshi's experimental results they conducted at NASA. And the opposite of that is invisibility, which is basically can photons pass through gaps in the material, and as if that material did not exist. This is purely from a probabilistic point of view, not taking into account the electromagnetic wave function, which is a slightly different phenomenon. So on this, similar to shielding is resolution. You have an object that obstructs and the wave comes across Resolution basically means that the object is big enough compared to the wavelength that it reflects the photon back. Whereas wrapping, which is the opposite, it's called transmission, but transmission is usually used in the sense of coaxial cables and nanowires. So I chose to use wrapping because it could also be bigger objects. Like radio waves will just pass through almost anything. So, which is the opposite. You have an obstruction there, and will it pass? Will the probability function wrap around and pass through as if it didn't exist? So that's what wrapping is. And they all obey the same formulas, but depending on where this big R and the small r is. And so one of the conclusions is that all photons are the same. They are the same structure, except that how they interact with matter depends on the relationship between the radius and the geometric structure of particles, of the objects external to the particles. Okay, so now what we have is basically there's only one photon, and it looks like different things because we have given them this different names for different wavelengths. Okay, so talking about probability fields, when you this comes back to the reason why I'm bringing this up now is because I needed to explain an experiment later. If a photon hits a molecule or an atom and it localizes, physics does not know what localization is, but it's a concept. The mechanism of localization. If it hits it at random, you'll see the black spots are the photons that are localized on this material, which consists of pentagon-shaped molecules, and they are more or less evenly, randomly distributed compared to here. So when you look at the point spread function, the centerpiece is called the airy disk. I found that out talking to people. The whole thing together is called the point spread function. So if you look at the point spread function, there are clumps of white and clumps of black. And this clumping is independent of the technology of the exposure surface, whether it was grainy films from 150 years ago when these sort of experiments were done, all the way to CMOS, all the way to the CCD cameras we're using right now. It's still similar clumps of black and white, which tells us that the molecules are correlated. So if we have a localization on one atom or one molecule on a surface, the likelihood, the probability, I shouldn't use the term likelihood because that's a technical term in statistics. The probability of the next photon localizing close by is much higher than it is away. That's what correlation means. So therefore, we see these clumps of black and white because it's a property of the material and not of the photon itself. Now, the analysis I did using the probabilistic wave function, one of the things I found out was that the phase angle, let's say 90 degrees here, the phase angle is directly a function of where it localizes. So if the photon hits the top of the pinhole at 90 degrees, it will the angle at which it localizes will be 90 degrees. If it hits it at a 45-degree phase angle, it would be 45 degrees on the screen. So we can tell what angle the photon interacted with the pinhole. What phase angle the photon interacted with the pinhole. And also the other thing is that there are extreme black spots, black regions where the photons don't exist. That's because part of the reason is due to the interference pattern with the pinhole. The other reason is that when the wave is on the positive side, it localizes at the top. When the wave is on the negative side, it localizes on the bottom. Okay, so that leads us to Chia and Nim's experiment. What they did was, diagrammatically, conceptually, it looks like this. There's a photon source. One path passes through a glass slab. The other path passes through air. They bring it together with mirrors, and then they observe a diffraction pattern. So what their axioms are in their analysis is that the photon travels along this hypotenuse. And so it should reach an extra time here. And the glass slab, which is the source of tunneling, because with the Schrodinger wave function, the tunneling is in front. The photon tunnels ahead. Whereas with an orthogonal wave probability disk or space wave, the photon will tunnel orthogonally because the probability function is orthogonal. So with their axiom that the tunneling is ahead of time, what they have found was that the time to go from photon source to glass slab all the way here is shorter than expected to measure this distance. Is shorter than expected. Give me a minute. Yeah, so these two guys, I couldn't find Gunther Nim's original papers, but I found write-ups on it. And they said that the photon was traveling between 1.7 to 4.7 times the velocity of light. That means it was actually moving faster. The photon was moving faster. So that's tunneling. No, but if you look at the probability function as orthogonal, then the tunneling is orthogonal. So the photon is traveling this horizontal distance and then tunneling across to the edge. And how they find out is by looking at the diffraction patterns. And so what you're seeing is that this velocity should be this velocity here through the air gap should be smaller than the velocity through the glass slab, because this distance, this radius is so much greater than the glass slab thickness. You see it as a faster than velocity of light. So that is the critique of this experiment, that they're actually not. If tunneling is forward, then that's a possibility. But if tunneling is orthogonal, then everything is normal. There's nothing traveling faster than light. It's only a localization that's happening within the disk of the photon's probability, and it occurs according to the probabilistic wave function. Okay, now the next piece is that Krennikov basically states that Bell's theorem rejects only local hidden variables, preventing faster than light communications. But when we take into account Roy Choudhury's requirement for a richer space-time, then, and we look at these experiments, then we can say that using the probabilistic wave function and photons being structures of space-time and subspace, then we can say that Bell's theorem is a special case because there are probabilistic hidden variables and there are space hidden variables, either due to the envelope function or the space wave. So when you keep the space wave the same, this is a model. When you keep the space wave the same, but you change the envelope functions, have different envelope functions, then you get a diffraction pattern that looks like the figure in the top right hand, left hand side. But if you keep the space wave the same and the envelope functions separate, then you have two needle-like structures, which means you can tell which part of the photon structure is producing the entanglement. And therefore, when we look at all our diffraction patterns, they're closer to the figure at the top. They do not look anything like the figure at the bottom. So we know that entanglement is due to the space wave. That's that wavy flat panel that has amplitude and frequency modulation. Okay, so applications, what can we do with this probabilistic wave function? Utlan, I think his name is Utlan. I have he ran some modeling with quantum theory and of nanowires in silicon oxide substrate, and he came up with a set of results on how the electric field disperses from the nanowire all out into the silicon oxide substrate. And I said, okay, let me try see what happens. Originally, I used the Var-Gamma distribution, but later I came back when I finally settled on the probabilistic wave function. I repeat all those modeling with the probabilistic wave function. And it is basically gives the same results or equivalent results to quantum theory's wave function. This is the nanowire, and the difference is in his model, he shows a very bright center in the nanotube, a nanowire, whereas I used classical radio wave antenna. There's nothing inside the antenna. It's all the field is outside. And so when there's nothing inside, this is the shape of the electric field that you get outside the nanowire. And this is the cross section of those. And this matches exactly equivalent to their work. So that's another thing, that the probabilistic wave function is just as good as the Schrodinger wave function in explaining things, but it is much simpler and easier to use. And the final thing that I put together was that you should be able to use electric field or a magnetic field to change the shape of this pattern, to change the probability distribution, to deform the probability distribution of the photon. And the total probability of a photon traveling in confined space is approximately 2 over the square of the maximum amplitude. And the lambda, the wavelength, is 4 times square root of epsilon times by the maximum amplitude. This relationship between the electric field magnitude, the maximum electric field amplitude, and the wavelength of the photon is not known in quantum theory. There have been experiments where they have tried to pin it down, but they have not been able to pin it down, which we now use this to provide some insights into Scheuer's M drive. There was something I had forgotten to tell you. Maybe I'll recall it later. Okay, now let's look at Scheuer's M drive. Oh yeah, I know what. So what this equation down here, lambda is equal to some function, some linear function of electric field amplitude, is that as the electric field amplitude increases, the wavelength increases. As the electric field amplitude decreases, the wavelength decreases. So you get a higher frequency. It's like, it's what is in effect happening is when the frequency increases, the photon is moving its electric and magnetic field energy into photon energy. And when it decreases, it's moving it back into electric and magnetic field energy. That's why I say there's only one photon. And how we observe it depends on the geometric structure. And this becomes a key piece of insight into how Scheuer's M drive works. Okay, now Tajma, Neuenzig, and Weikert provided a critique of all the M drives papers that had been published, and they have done an excellent critique of the experimental errors. But they even say, this is something that caught my attention because I've had that problem before when I've been deconstructing other people's papers, is that some of the papers do not explain enough in sufficient detail to be able to reproduce the experimental results. So this is Tajma's and al.'s experimental setup taken from their paper, and this is Scheuer's M drive taken from Scheuer's SPR Limited website. So you can see this is the whole contraption. In effect, if you compare what I'm doing and what Tajma and his team were doing, is that they were looking at everything in this box except the M drive, and I'm not looking at anything in this box but the M drive. So I'm looking at how the M drive works. And the discussion is more about, given what I've done in the past, how can we improve the M drive to show that this is a real, this is possibly a real technology, and how can we improve it so that somebody can go out there and build this that actually works. Okay, so nature's photon transformation. Do you know that every nanosecond or femtosecond this is happening? A red photon goes into a region of space-time and comes out a blue photon. Anybody got any ideas what it is? It's called gravity. Your source of the photon energy is, on one end, you have a region of space between the photon and the gravitational source, where it changes as the photon is falling into the gravitational field. It transforms from a lower frequency red photon to a higher frequency blue photon. It's happening. It's happening all the time. Billions and billions and billions of this. The reverse is also true. As the photon leaves the source on a planet or a star, it's transforming from a blue photon to a red photon. So why do people say that momentum exchange is not conserved? At this end of the region of space, you have one set of momentums, and the other end, you'll have another set of momentum. But it's not an issue about conserving momentum, because if you look at Scheuer's experiment, conceptually, it's basically the source is at the back end of the drive, and the red photons come in, the longer wavelength microwaves come in, and shorter wavelengths microwaves come out. So that's the region where the energy transformation is being done. So the problem with momentum analysis is that it is Newton's third law of motion is only applicable on contact. If it is not contact, you cannot say a star out there and I'm down here, we have to conserve momentum. No, it needs to be contact before you can apply conservation of momentum. Okay, this is taken off Wikipedia, but it shows you how electric and magnetic field lines move through a microwave cavity. The bright spots are the positive and the dark spots are the negative field. And this is not a standing wave. You see, it's a moving wave. Okay, so if we look at Scheuer, he had two requirements, which is to manage Q, to prevent energy loss, and the resonant cavity, which means you want a standing wave in here. But as we have seen in the earlier discussion, if there is a phase shift, you cannot get a resonant wave because it disrupts the whole reflection process. And so in this analysis, we're using, like in the microwave oven, we are assuming that there's no phase shift. So here we can calculate and place what is the momentum. F is the front end and B is the back end. That's a momentum. And then let me go to the next slide. Or there's a voltage at each, depending on the electric field of the photon at that point. Okay, so by this equation, lambda is equal to 4 root epsilon EA. And if we set the voltage at the back end to be equal to the voltage at the front end, so that there is no current, at least between the two ends, there's no current, to minimize that current, basically to minimize the energy loss. Then we can show that the relationship, see, in Scheuer's microwave, he had the microwave source coming out as a pipe in somewhere in the middle section of the resonant cavity. So I will label that as 0, and the back end is with subscript B and the front end with subscript F. So the momentum exchange can be defined as this, as a ratio of the position of this centerpiece with respect to this end piece and that end piece, the back and front end piece. So you can show for a pair of the net momentum for a pair of photons, one hitting the back and one hitting the front, is simply a ratio of the original lambda wavelength and the radius of this cavity. That's it. So Scheuer's structure is not a specific radius or conical shape. It can be any shape. It can be a flat conical shape, almost flat conical shape, or it can be an extended long conical shape. So this is the general form. Okay, and then when you look at the model results, these are the bands Q, U, V, E for these wavelengths. This is a mid-band wavelengths for the respective microwave bands. And this is the total length, which is from the O, this is the back, and this is the front F. So you combine the two, you get the total length. This is the position of O in the microwave. To get, let me move this. Okay. This is, and that's a momentum change between the front and back, and for two photons going in that way. So you get for, or for this L 2.6, that's 2.6 millimeters. No. Yeah. Okay. It's to the -2. Sometimes I lose track of the decimal places, but that's why I use Excel, so I don't have to worry. So you see, you have to start, because we want the electric field at maximum to get the height. There are two reasons. One is to get the voltage, because the electric field is voltage divided by distance. So we have to get the maximum electric field, we start at a phase angle of 90 degrees. And also the maximum electric field increases the possibility of interacting with the material. So that's why we want the wave to start at 90 degrees. So it's essentially a cosine wave, and the wave to end at plus or minus 90 degrees. So we find that the momentum change between two photons traveling in opposite directions is given by these numbers. And for the thrust, Shoya used T as thrust, so I'm sticking with that so we can compare. It's given by the change in momentum over change in time. This gives us the change in time. It's purely a function of the structure of the resonant cavity. Compare that with Shoya's equation, not using group velocity, because if we're using group velocity, it's a different comparison. I'm comparing apples to apples, and this is the momentum per unit area. What it's HF, N for number of photons. I think it's times by C. If you look it up, it's in his paper. It's available on SPR Limited website. So, so this is for the U band. This is for the Q band. You can see it is possible to do that, provided there's no phase change, and that's the momentum difference across as the wave changes wavelengths, because of the voltage. We're keeping the voltage equal. Okay, so when we want to optimize for the M drive, what we want to do is the L naught. We want to okay. Here, what I did was optimize in this first set of model runs. I optimized the position of L naught, where the L naught should be. That means the tube of the cavity where the microwaves come out. We need to know exactly where that position should be to maximize the difference in the momentum. Okay, so it changes depending on your wavelength of the microwave. Okay, so here, what I did was here I said L naught is basically 0, and I put, instead of having the tube where the microwave comes out in the middle of the resonant cavity, to get and put it at the back here. Why did I put it at the back here? Because I want to be able to control the phase at which the microwave comes out so that it's 90 degrees. And this is the total length. I go all the way from very small to almost very flat surface to something that visually approximates the size of Shoya's M drive. and the momentum exchange is the same, exactly the same for that length. You can change the length. So the important characteristic is not so much the length, the phase angle at which they bounce, and the radius. And it has basically, if you set it for 90 degrees, it's a cosine and not a sine. If you look at most diagrams of standing waves, they are sine functions. They start from 0, oscillate, and then come back to 0. So we are on the last slide. So how do we make improvements to the M drive? Basically, the black surface must be highly reflective, because this is the reflective surface. The momentum exchange happens before and after reflection. It can be written down as this equation, and the momentum exchange of an absorptive surface. We want maximum absorption on this surface because this absorption is governed by this equation. So depending on how the reflection or absorption is happening, you have two different equations. So you have the net momentum here. So to maximize the absorption here on the front surface, you want a highly absorptive surface, a black surface, but NASA has come up with this quite some, maybe 10, 15 years ago, NASA invented a black called extreme black. And I know about it because when I was living in Colorado, I met these people, and for the life of me, I've forgotten their names or the name of the company, but they were producing this extreme black for commercial use in Colorado. So I know that there is such a material that exists. On the back surface, you want it to be an extremely shiny surface so that it reflects as much of the microwaves as possible. And like I was saying earlier, you want the source of the entering microwave to be at 90 degrees phase angle. So you want to be able to adjust this back end microwave pipe, cable, whatever you call it. I'm a theoretical engineer. I'm not a practical engineer. To be adjustable so you can make this 90 degrees, and then you only have one parameter to watch out for, which is the length of this cavity. As long as you have this cavity exactly correct, you don't have to worry about a microwave source that comes out here and then you have misplaced it slightly. You cannot get it the phase right. So you want it at the back here. And then you want to make sure that you do get a standing wave. Note that you have to use materials that are not that do not produce phase shifts on reflection. Okay, so the last word, what are we doing here? You have a low frequency wave coming in, coming out as a high frequency wave. So what we're doing is over unity. That's the only way nature allows over unity. Thank you for listening to my talk.
Wonderful. Benjamin, thank you so much. So let me do this. I want to go to gallery view, and everyone please, and let me see. You know what, let me stop your screen share. Okay. And everyone, please put your hands together. A giant thank you, Benjamin Solomon, and a tremendous, incredibly detailed presentation. So Benjamin, thank you again.